All right, so today's notes are on rational functions. Our content objective is to identify properties of rational functions, and our language objective is to correctly describe the type of discontinuity of a rational function. So first thing I want to do is define what a rational function is. So actually, we learned about reciprocal functions first. They are a subgroup of rational functions. So rational functions are when you have one function divided by another, or two expressions being divided. So it's just any expression over another expression, and the domain restrictions are when the denominator would be 0. So a rational function is when two expressions are divided and your domain is restricted by when the denominator would be 0. So as we mentioned in our language objective, we're going to talk about how they can either be continuous or discontinuous. So continuous graphs have no jumps, breaks, or holes in them. So that means that it's just a straight, clean line, or not straight, but a line fully connected, no stops in it whatsoever. And I drew an example here. So this, we have x squared over x squared plus 1. Here, there are actually no asymptotes, no holes, no jumps. So we saw in piecewise functions, we can jump from one space to the next in a graph. And we saw in our reciprocal functions, we also have asymptotes. Continuous graphs don't have any of those things. They are just clean, straight through. Discontinuous graphs, on the other hand, are like the ones we were just talking about. So they have jumps, breaks, or holes, asymptotes, those sorts of things occur on discontinuous graphs. What's interesting about discontinuous graphs is that they can have holes that are actually removable. So sometimes you'll have a discontinuous graph, but that discontinuity is removable. And this occurs when it is at one specific coordinate. So I give you an example here. So this graph is not continuous because there is a hole right here because these would actually cancel out. So if you actually, like if you had this rational function, what you would be able to do is cancel those out. But because the original function had that x plus 2 in the denominator, -2 would still have a hole in the graph. So it's still discontinuous, but it's a removable discontinuity because all you'd have to do is say at this point, x now can be -2. It's fine now that we've canceled that out, and then that would remove the hole. But it still is technically a discontinuous graph until you make those adjustments. They can also be non-removable, and this is more along the lines of what we were working with the reciprocal functions. These are when you have asymptotes or jumps like we did in piecewise functions, where there's no way to fix this graph so that it doesn't have this break. Like this break is a key feature of this graph. There's no way to change that about it to make it continuous. It will always have these asymptotes. So I'll give you an example of that here. This graph has a non-removable discontinuity because it has two asymptotes here. There's no way we can cancel them out in this equation. There's no way around them. So those are non-removable discontinuities. So I'm going to flip the page to go on to the next part of what we're doing today. And this is actually the key stuff that we're going to be focusing on, is determining the asymptotes in these functions, so or solving out for them. So the first one, we have vertical asymptotes, and this we've talked about before. They occur whenever the denominator would be equal to 0 and the factor can't be canceled. So we know that we're going to have a discontinuity at any value that would make the denominator 0, but the asymptotes occur when they can't be canceled. So there's still going to be a discontinuity at every point that makes the denominator 0, but there's only asymptotes at the points that make it, or that are not removable. So here in our first example, I know that if x was equal to -2, or if x was equal to -3, I would have vertical, or my denominator would be 0. So I have vertical asymptotes. I have 2 of them at x equals -2, x equals -3. So because those are the values that make my denominator 0, that's where I'm going to have my vertical asymptotes. So in a lot of today's, or the work for this lesson, you'll be practicing solving for when the denominator would be 0 to figure out your vertical asymptotes. So you're going to be solving when the denominator is 0 to figure out vertical asymptotes. Or what you could also find is that they might cancel. So you're going to have, in this case, we have x plus 1 over, or times x plus 2 all over x plus 1. And you might notice that those can actually cancel out. So I'm left with just y equals x plus 2 once those cancel. So what that means is there's no vertical asymptote because that canceled. So the key here to remember is there's no vertical asymptote, but there is a discontinuity at x equals -1. So because x equals -1, my denominator would originally be 0. I'll still have one of those holes like we saw in our removable discontinuity. I'll have a hole like this in our graph because there was originally a value of x that would make the denominator 0, but there's not going to be a vertical asymptote because it was able to cancel out. So there's no vertical asymptote, there's just a point of discontinuity when x is equal to -1. Or point discontinuity. Sorry, I should put that. A point discontinuity when x is -1 because it was there originally. So that's it for vertical asymptotes. Again, just figuring out when they're 0 and if they cancel or not. That tells you everything you need to know about the vertical asymptotes and discontinuities. Horizontal asymptotes have a few more rules. So horizontal asymptotes can only occur once at most on a graph, and you determine where it is by looking at the degree of the numerator and denominator. So there's 3 different scenarios we can work with here when looking at the degree of our numerator and denominator. So I set up a situation. If I have a times x to the m over b times x to the n, I can have 3 situations. Either m can be less than n can be greater than m, n, or m is equal to n. So I gave examples over here, and we're going to talk about what each of those rules is. So if the numerator degree is less than the denominator degree, so if m is less than n, the numerator is less than the denominator, then I'm going to have a horizontal asymptote at y equals 0. So if the denominator is greater, or if the numerator is less than the denominator, my asymptote's just at 0. It's pretty easy. So if I'm looking at this example I have here, my degree here is 1, this is 2, so 1 is less than 2, which means I have a horizontal asymptote at y equals 0. So because this degree is less than this degree, my horizontal asymptote is at y equals 0. The next situation is if the numerator is actually greater than the denominator. So if my numerator degree is greater than my denominator degree, then there's going to be no horizontal asymptote. So the way I think of that is if the degree on the top were greater, then then I'd actually be able to cancel and have just a normal, like if you think of here, and sorry, in this example, I had a degree of 2 because I had 2 x's versus 1. And so I'm able to cancel 1x and just have a normal looking or a linear type or simple equation. So if your degree in the numerator is greater than denominator, so in this case, 3 is greater than 2, I can say there is no horizontal asymptote. So if your degree in your numerator is greater than the denominator, there's no horizontal asymptote. Last but not least, if our degree is equal. So if I have in this case, I have a square over a square as the highest degree here, then the horizontal asymptote is going to be at a specific value. It's going to be at y equals the ratio of those coefficients. So that's why I put those there. It's actually going to be at y equals a over b. So if I look at my example here, I see my degrees are 2. So 2 is equal to 2. So what I'm going to do is take the leading coefficients, and that's where my horizontal asymptote will be. So I'm going to have a horizontal asymptote at y equals 2 over 5. Because the ratio of the leading coefficients, so the coefficients of the x squareds, tells me where my horizontal asymptote will be. So that's what we have for today. That's all we're going to go over for now. Make sure you write down any questions, comments, or concerns you have so we can go over them together in class.